I would like to introduce our certification committee. Serhiy Stiranko, the chairman, Doctor of Technical Sciences, professor, vice rector for research of Igor Sikorsky, Kyiv Polytechnic Institute. Natalia Sakhnenko, industry expert, invited guest, associate professor, Doctor of Physical and Mathematical Sciences at Igor Sikorsky, Kyiv Polytechnic Institute. Rostislav Hrenev, Doctor of Sciences in Physics and Mathematics, Professor, Head of Department of Applied Mathematics and Statistics at Ukrainian Catholic University. Alexey Molchanovsky, Senior Lecturer, founder of the program, Master's Program in the Data Science, Chief Innovation Officer at the Ukrainian Catholic University. Vadim Yermolayev, PhD in Physics and Mathematics, Professor at the Department of Computer Science and Information Technology, Head of the PhD program. And I would also briefly remind you about our today's plan. So we will start with 2 presentations, then we will have 20-minute break, then 2 presentations again, and 1 hour break for the lunch. Then we will proceed with 3 presentations and 40 minutes break after that. And we will conclude with 2 presentations. And after that, we will announce the results for today's Master Defense. And we will start this Master Defense session with Yury Rozyayev, who was supervised by Oles Dobosevich, and he will be presenting EULA, your unique language adapter for localizing Japanese scene text into Ukrainian. Yura, please.
Can you hear me well? Good morning, everybody. My name is Yury Rozyayev. Thank you, Ruslan, for the introduction. This topic is special in many different ways, but first and foremost, it's special to me personally, as I was the one who suggested it. I came up to Oles Dobosevich with the idea, he liked it, and agreed to become my supervisor, so I'd like to thank him for making this possible in the first place. I think I have to start by addressing a question that many of you probably have in your mind right now, well, at least those who haven't seen the presentation before. And I think that the question is Japanese? What? Indeed, you heard it right. Japanese language is a big part of this research. And the reasoning for that is both simple and complex at the same time. I hope that the complex reason you will understand as we go. But the simple reason is that I studied Japanese. In fact, I've been studying it for over 1,000 days now. And the most common question I get is why? Why are you doing this? Why Japanese of all languages? After all, it's so difficult and different from any other languages. And another question is, where are you even going to use it? Well, apparently in my master thesis at the data science program. How come you didn't guess? It's true that Japanese is a unique and extremely difficult language, especially when you compare it to languages like Ukrainian or English. And it's quite complex. This meme here showcases one of the difficulties that beginners face with when they first start learning Japanese. Particularly, the order of parts of speech is different. Verb comes at the end. But if you add more words to it, things get really messy really quickly. And this was just the tip of the iceberg. There are many more differences that make the Japanese language so distinct. To name just a few, these are the Japanese writing system, the fact that it can be written vertically, and the dense semantics of the language. Here we cannot see that, but in Japanese, complete ideas or whole sentences can be conveyed using just a few characters. And also, did you notice that the Japanese sentence does not have any spaces in it? Cool, right? Imagine reading it when there will be no colors. Actually, this property is important. I want you to remember it for later reference. So the most important part of the Japanese language that I need to explain you is its writing system. It consists of hiragana, katakana, and kanji. Hiragana and katakana each contain over 80 characters. Every character represents a single sound or a syllable. For example, a, I, U, E, O are like vowels, but then when you combine them with consonants, we get something like ka, ta, ga, na, o, and many more different characters. Kanji, on the other hand, is a script adopted from the Chinese language. Each symbol represents some meaning. For example, kan is China, and G is a character if you look at them independently. But if you combine them together, it creates a word Chinese character if you translate it literally. However, these translations are not always like that. Number of kanji characters is quite large and actually practically uncountable, as dictionaries show that from 12 to 50,000 different characters. And unfortunately, these little fishes are not part of the characters. But on the good side, there are around 3,000 characters used in modern speech. So it makes our life much easier. Since all of the three scripts are extensively used in the modern language, we did not exclude any of them. So we are working in our research with all of these scripts. The last thing I need to explain about Japanese is actually related to the name of this research, Yula. Basically, in Japanese, there is no distinct sound for ra and la. So it happens that when you write it in Japanese, it is written and sounds exactly the same as my name. It's totally coincidental, and I definitely didn't spend a whole day coming up with this Easter egg. Anyway, let's move on to the main topic of this research. In our work, we process syntax. Syntax refers to text that appears in natural videos, in natural images or videos, and it's often integrated into real-world environments. You can see examples of it on the slide. It's often integrated into real-world environments and stuff like signs, labels, street names, and any other written content visible in an outdoor or indoor setting. Syntax is typically hard to process because of factors like distortion, varying fonts, lighting conditions, and occlusion. Syntax editing is a computer vision task that involves replacing the original syntax with some desired content. And the main goal to do so is to retain the styles, background, and textures of the original image and ensure the realistic appearance of the generated image. Syntax adaptation is the main task that we are working with in this research. It extends the scope of syntax editing by introducing a different target language into the process and presents several additional challenges, including different writing system, handling limited contextual information during translation, deciding between translation and transliteration, adjusting varying text length to fit the spatial boundaries, and preserving the cultural context of the original text. Now you may wonder, why do we need this in the first place? The main practical application that we see for the syntax adaptation is in the localization of foreign media, such as movies, TV shows, or anime. Studios that are working on the adaptations often operate with limited resources. So doing the syntax adaptation for them manually is virtually impossible due to the sheer amount of content that needs to be adapted. At best, syntax receives subtitles. Here we have an example where one of the studios actually inpainted the translation on the image on the left, but in the same show, another frame with syntax they completely ignored. And this is what actually happens quite often with the syntax, where it doesn't have any subtitles even. So many fun and interesting details get ignored, they get skipped, and the viewer is unable to know them. Automating this process would alleviate those resource limitations and allow to enhance the immersion and viewing experience for the viewers. Now that we know where it can be applied, we should actually answer the question whether there is an actual demand for it. This graph shows a trend of Google searches for anime in Ukrainian starting from 2022. We can see a steady growth here, and this proves that interest in this topic is actual. Correlated to the growth of demand for anime in Ukrainian, the search results also increase. And this proves that the amount of Japanese media published in Ukrainian language is also growing. Therefore, supply and demand of Japanese content in Ukrainian confirms the practical relevance of this research and shows that the potential to reach a broad audience. Now it's a good time to look at the existing research that has been done in relation to this topic. As this is a relatively new field, the number of available publications is rather low. We've performed an exhaustive search and were able to accumulate 16 different papers and constructed this comparison table. By analyzing the table, you can see that the first publication was made in 2019. 9 of the 16 papers are open source, and actually only 3 of them show cross-lingual potential. Two papers address the syntax adaptation task explicitly. However, only the last one, Vstrans number 16, is open source. And another interesting observation is that diffusion models, even though they are getting popularity over the last few years, they usually don't focus on the syntax editing task alone and include it as a part of the task. So it's unfortunately not as relevant for our research at this moment. This analysis helped us to identify a critical research gap in the field of syntax adaptation, in particularly between the pair of mutually unique low-resource languages. Here it's important to note that when you consider the Japanese language and Ukrainian separately, they can be called high-resource language and medium-resource languages on its own. But if you combine them, like if you consider them as a pair, especially in the context of the syntax tasks, they are still considered low-resource language pair because there is almost no paired data for these languages. So it's also important to mention the commercial solutions for syntax adaptation, the most famous one being the Google Translate for images. We've used it to adapt the image from before, and we can see that the translation quality is actually pretty good. However, the style transfer and the original text erasing is lacking. And considering that it's a proprietary solution, it further proves the need for continued open research of this topic. As I previously mentioned, the only open source paper addressing the syntax adaptation is Vstrans. In the paper, they tackle the problem of automatic syntax adaptation by proposing this cascaded framework. And it consists of state-of-the-art modules for OCR, machine translation, and syntax editing. However, their framework is focused heavily on Hindi and English languages, and it's not robust enough to be easily adapted to other languages. Therefore, despite the advancements in syntax editing, current solutions largely center on English language and Latin scripts. Therefore, our work focuses on creating a baseline for automatic syntax adaptation from Japanese to Ukrainian as a case study, but so that it can be easily adapted to other languages. Core problem of this task consists of optical character recognition, essentially detecting and recognizing the Japanese syntax, then translating it to Ukrainian using machine translation, and performing syntax editing for the style transfer. Our hypothesis is that the existing models, architectures, and approaches are sufficient to create such a baseline, and we hope to achieve performance on par with state-of-the-art models that were developed for simpler scenarios, like for English only. Now let's look at the research scope and the limitations that we imposed. Several design decisions were made to simplify our development of the baseline and ensure its feasibility. These include off-the-shelf, meaning that we rely on existing models, same as in Vstrans, though we do adapt them in for our case study where needed. We are not explicitly aiming to improve them. State-of-the-art is not guaranteed because our goal is to establish the baseline. And while we do try to select the best models at each step, the absence of specific benchmarks for this pair of languages make it rather difficult. And creating such benchmarks would be like a completely different task alone. Next is data simplifications. To simplify an already complex task, we decided to focus on only horizontal and short texts. And more importantly, we are only working with synthetic data here, as no real-world data set for this pair of languages and for this task exists. Lastly, the nature of our system is one-sided, meaning that we do localization from Japanese to Ukrainian language only. And the other way around is only left for the experimentation stage, but I will get to that later. While these limitations help focus the study's efforts, they also provide like a foundation for easy improvements in the future. The research plan is divided into 4 main stages, and each stage addresses key aspects of the specified problem one by one. Data acquisition is the first one, then we go to pipeline development, performance evaluation, and generalization assessment. Let's dive deep into each one. In data acquisition stage, we prepared a synthetic Japanese-Ukrainian syntax dataset, or JAST for short. And the main goal of this dataset was that it should have been sufficient enough to support the training and evaluation of our implemented framework. To generate this dataset, we adopted the SRNet data generation framework, which was first introduced in the first paper called Editing Text in the Wild, in 2019. And there are almost 150,000 training samples and almost 15,000 validation and test samples in the dataset. These numbers are not round because there were some duplicates during generation that we had to filter out. For every sample, a total of 5 images are produced. First is the randomly picked background image, and then source and target syntax images, along with the source and target text masks. In addition, a file contains both source and target texts. The data generation framework requires 3 things to work. First is the shared collection of fonts. In our case, it's extremely important because if a font is not, if a font does not support both Japanese and Cyrillic, we wouldn't be able to render the same word in the same style. We were able to aggregate 113 shared fonts, but a lot of them didn't support all of the Ukrainian letters, such as I, Y, Ye, and G. So we developed a pre-processing algorithm where for every unsupported letter, we replace it with a similar one. So for example, here in word Дякуємо, we replaced Ye with E for this specific font. So the second requirement is the word corpus. For this, we used a popular Japanese words dataset, which contains over 30,000 different words, and translated into Ukrainian using our machine translation module, and used it to render the text on the images. Last requirement is the background images collection, which we simply reused from the existing paper, and it contains over 8,000 different background images that are later cropped out, a small portion of it, and used as the background. So following the general approach introduced in Trans, we built our end-to-end pipeline that we call EULA. Here is the overall architecture presented on the slide. And this pipeline integrates syntax recognition, syntax detection, recognition, translation, and editing modules. It's designed to be highly adaptable for other language pairs and introduces human-in-the-loop mechanism for the first time in syntax editing research. The overall flow of the pipeline is as follows. The first input image goes through the optical character recognition module, where if HATL is enabled, a user can already select and choose whether he wants to proceed with the following text or decline it, discard it. It's useful for cases when you don't need to adapt stuff like symbols or numbers. After that, optical character recognition produces bounding boxes and the recognized text. If there is multiple texts, the next steps are simply repeated sequentially. On the next step, the recognized text is passed through the machine translation module, and the bounding box is cropped out so that the next stage of syntax editing can focus on the region of interest with the text only. The syntax editing module receives the translated text and the cropped out image as input and produces the adopted image as output. And here the HATL mechanism for machine translation allows user to select whether he wants to accept the automatic translation or specify his own target text for the output, as well as for the syntax editing. He can decide whether to save the final result or to completely discard it if the quality is unfortunately not good enough. If he decides to save it, then the final result is resized back to the original sizes and merged back into the original image. So let's now look at the each module a bit deeper. Since our goal was to, first is the OCR module. Since our goal was to create a solution that is easily adaptable for other languages, we focused on multilingual and open source OCR engines. We considered a few of the most popular ones and selected Puddle's PPOCR v4 system as it demonstrated higher accuracy and had significantly greater community adoption with over 50,000 GitHub stars compared to the alternative solutions. However, we saw that the system often struggles with images of small resolution. So we implemented a dynamic scaling of the image up to 4 times of its original size using a basic interpolation method, which helped prevent this issue. Next module is the machine translation module. It's the second stage of the pipeline. And to meet the goals of a replicable framework, we again focused on multilingual models. We evaluated several state-of-the-art models. As for the LLMs, they can also be used to perform multilingual machine translation, but we left them out of the scope of this research. And same goes for the proprietary translation APIs like DeepL or Google Translate, as they are under paywall. For the rest, the evaluation was relatively simple, as there is no specific benchmark for this part, this pair of languages. We simply tested a few simple words like hello, thank you, or goodbye. And among the evaluated models, we selected M2M100 with 1.2 billion parameters, as it provided the best balance of quality and efficiency. However, direct translations were often unsatisfactory, so we introduced an option to use English as a pivot language and the previously mentioned human-in-the-loop mechanism to manually correct translation when needed. For syntax editing, we had to train our own model, as there is no such model for Japanese to Ukrainian syntax editing. And for this, we used latest GAN-based architecture. It's called Mostel, and it consists of 7 subnetworks. I won't go deep into the architecture, but in general, almost all syntax editing models follow the erase and write paradigm that was first introduced in the same editing text in the wild paper. The paradigm basically makes separate modules. One is erasing the original source text and restores the background. Another module transforms the target text to the desired style, and last module combines them together. Mostel builds on top of its predecessors, and most importantly, it introduces semi-supervised learning approach. However, as we don't have real-world data in our work, it's not relevant for us at the moment. So now let's look at the evaluation metrics that we used. First is the OCR. As mentioned earlier, there are no clear separators in the Japanese between Japanese words. So the only 2 suitable metrics that we can use are the character error rate and match accuracy. SER measures the edit distance between the predicted and ground truth character sequences and is normalized by the length of the ground truth text. Match accuracy, on the other hand, is the stricter metric, which gives a sense of how often the OCR model produces completely correct outputs. Now we can actually look at the results for the OCR evaluation. Our OCR module was tested on the validation set, and it was able to successfully process around 11,000 samples with the total failure rate of around 24%, which means that it didn't detect any text at all in these cases. This failure rate is relatively high and suggests that the dataset contains a significant number of challenging samples, for example, the ones shown on a slide. To account for this high failure rate, we computed the average SER and match accuracy for both including fails and excluding them. When failures are included, the results are pretty bad. Average SER of almost 0.5 means that every second character is wrong. But when we exclude the failures, it shows that the results improve, but they're still not great, implying that the dataset still contains a lot of challenging samples. Upon further investigation into the distribution of the errors, we saw that in most cases it failed to detect some part of the word, and in other situations it confused very similar characters like the ones on the slide. And surprisingly, we found that the translation module was able to sometimes correctly translate text with such errors. However, as we didn't perform complete machine translation module evaluation, we cannot conclude this behavior, and the evaluation was not done because of the text simplifications mentioned earlier. Finally, we get to the syntax editing model evaluation. Visually, we can see that model replicated the general style quite well, including color, stroke width, and spatial parameters of the text. However, the intensity of the generated text appears lower than the source and target. Additionally, when handling more complex font as the one on the below, the quality of generated image degrades. This is likely due to a lack of complex fonts in the training data. For the quantitative metrics, we adopted the same ones as in the original paper. Evaluation was performed every 10,000 iterations, and in total, 300,000 iterations were done. First metric is mean squared error, where lower values indicate better reconstruction quality. The evolution of this metric is shown on the graph. Second metric is peak signal to noise ratio. It's derived from mean squared error and expresses the ratio between the maximum possible pixel value, which is 1 for normalized images, and noise level. And higher PSNR values indicate the better image quality. Third metric is SSIM, or structural similarity index measure. It measures perceptual quality, similarity between images, considering luminance, contrast, and structure. Here, the values range from -1 to 1, where 1 indicates perfect similarity. And last but not least, FID measures the distance between feature distributions of real and generated images using a pre-trained Inception V3 network. Lower FID scores indicate that the generated image are more similar to real images, and it's usually the go-to metric for generative tasks. To qualitatively assess the performance of our pipeline and to understand its generalizability to other scenarios, we performed a set of experiments. First, we evaluated our pipeline on a few dozen of real-world images taken from Google Street View. The results were surprisingly good, considering that we didn't have any real-world data in our training set. Next experiment was with more complex scenarios. Here we checked model's generalization on very small text, long text, vertical text, and also English. As expected, the model failed miserably in all of these scenarios. Last experiment was to check how a model performs in a reversed language scenario. So we have source Ukrainian and target the Japanese. It also, as expected, failed to erase the Ukrainian text properly and generate the Japanese text. However, in some cases, the results almost look similar to the target image, like on the first one, but in reality, it's not that good. Concluding all of the experiments, we see that EULA performs well for the task that it was trained for, but struggles in other scenarios. So future work is still required to address all of the limitations posed in this work and unlock its full potential. To this end, we make several key contributions. First, we create and release the Japanese-Ukrainian syntax dataset, as well as the code to generate it. Second, we introduce EULA, end-to-end modular pipeline that can be easily adaptable to other language scenarios. Third, we evaluate EULA to establish a baseline for the Japanese-Ukrainian syntax adaptation task. And finally, we obtain insights into our system's generalizability and assess its replicability to other scenarios. To summarize, this work marks an important milestone in the field of syntax adaptation for low-resource languages. This research extends beyond its academic objectives, offering direct application in cross-lingual content localization. Automating this process can streamline the production of adaptations and make them more immersive and engaging. We envision this as just the foundation for a larger project, which could even evolve into some standalone product. This will involve integrating video format, introducing friendly UI, and expanding the supported languages to enable the widespread use of the application. This is actually all from me. Thank you. Дякую за увагу, and arigatou gozaimasu.
Thank you. Anyone would like to start with questions? Madam, please.
Thank you very much for your insightful talk. Really enjoyed. I've been looking at your thesis. I've been looking at your abstract, epigraph. Are you really telling us that the work you did resulted in a fake and we have to value it accordingly?
Well, the word fake is referring to the generated image, synthetically generated image. So it's like fake in terms of it was not produced by human, but by AI, and yeah, kind of like that.
Are you generalizing to implicitly tell us that all the works related to synthetic data sets and broader to machine learning are fakes and should be valued accordingly?
It depends how you treat the word fake. As I said,
in a Japanese style. I mean, opportunistically.
Again, here I treated the word fake as like something not done by a human. So the actual, for those who don't know, in my citation, I don't recall it correctly, but something along the lines of the fake is of far more greater value, which means in relation to this work that the generated image by an AI is of far more greater value to the audience than non-translated original syntax. So if we consider fake as generated image not done by a human, then it emphasizes the fact that it's of far more greater value than it's a better thing than not doing anything.
Thank you for explaining. Of course, that was a sort of a warm-up question. More seriously, let us go back to your evaluation charts.
Which one?
To ask you, anyone. I'd like to ask you to explain which values are to the left compared to the chart to the right.
Yeah.
Why did you pick EULA 0.0107?
Yeah, sure. I didn't mention this during the presentation. I intentionally excluded it because it was too much to explain. Basically, as I said, we perform iterations. We perform evaluation every 10,000 of iterations. Considering the FID score that we obtained, the best FID score, we chose the checkpoint at the 29th step. This is the best value. So at checkpoint number 2900. At the 29th checkpoint, we got the FID of 10. And here the value for Mostel is just for the reference, because we shouldn't directly compare them because the language and evaluation dataset are completely different. So this is why there is a note. And it's just to show that our absolute values are in like kind of the same range, but we shouldn't compare them directly.
Just to elaborate a little bit more. No, I'm pretty sure that Mostel is the only indirect competitor which could be used for a sort of cross-evaluation in this context.
Yeah, of course not. We could have compared it to like multiple different models, but we are comparing here it with the original paper Mostel, on which the models like architecture, we took the Mostel's architecture. So this is why we're like comparing it to only this one. Again, there is no point in doing the direct comparison between any of them because this is the first work that directly addresses the topic of Japanese to Ukrainian syntax editing.
Yeah,
so,
this is understood. So please correct me if I'm misinterpreting what you're delivering here. EULA, it's very early to say that EULA has broken the state of the art in this task.
Well, we are establishing.
And if broke, what is the exact context where it happened?
Yeah, I cannot say that we are breaking the state of the art because we are basically establishing it because we are establishing a baseline. There is no specific benchmark for this specific task in the context of these two languages. There is no multilingual benchmark that includes Japanese and Ukrainian. So since this is the first evaluation done for these specific languages, we shouldn't directly compare it to just like English to English editing or English to Chinese adaptations that I showed here. So
okay.
I hope I answered.
Okay, thank you very much.
Yeah.
Thank you very much for your presentation. It's very interesting, and I know it's a very difficult problem. And you've shown us excellent results. I have a few maybe questions. Do you have any idea? So the main problem is a lack of this sharing alphabets for two languages. And actually, at the moment, due to lack of this data, your model has grammatical errors, right? If you write A instead of E,
yeah, kind of.
right? Do you know, have you any idea how you can fix this?
So
maybe.
Yeah, so Actually,
I know
let
it's
me-
impossible.
Yeah.
It's impossible, but
Not a
if you know.
Yeah, I've thought about it, of course. Well, initially, my assumption was that the grammatical error wouldn't matter as much, since I hope that the model will just learn to render pretty much any text. The way it works is when the model renders the initial target text. For example, let's say our model wants to render this дякуємо. It will render it with a font that supports all of the letters. So the initial image will have the yeah.
You mean lack of data in some fonts, not in
Yeah, in some fonts.
Okay, okay.
So it's
Okay.
like, if
It
I
works.
remember correctly, it was like
Mhm,
60% Cyrillic and the rest are Ukrainian. So we chose the font that supports all of the Ukrainian letters and most of the Japanese ones. And when we first input, when the model first starts to generate, it begins from this дякуємо similar like to this one, and then it like tries
I know,
to transform it to the target. However, my assumption was that these grammatical errors wouldn't matter, and it will just learn to pretty much map it correctly. What we saw is that it actually learned to map letter Y to letter E. So this is kind of a problem, and fixing it, I think, would require to balancing the dataset or even making a skew towards the fonts with towards data where the fonts with all supported letters are used.
Okay, thank you very much. And one more small questions about metrics. Your problem is, for me, is very similar for problem of style transfers. The style transfer have a lot of this definition have a lot of options. For example, you have corpora of text, example of font, just photo, and you can render this corpora in this font in this domain. Visual appearance of font style, frequency estimate with so-called Siamese networks with triplet loss, with contrastive loss. But you estimate the quality of images, just VID metrics is just estimate quality of all image in general. So you didn't
so
look in this direction?
those metrics are just for the evaluation of the generated images. During training, there are, as I mentioned, it consists of 7 subnetworks, and each subnetwork has its own loss. For example, there's 2, I believe, generative adversarial networks inside it, one for the background restoration module, one for the text modification, so it has its own GAN loss. Then there is the style loss, which uses, I believe, VDG model to do the style loss. Then there is one loss for recognizer accuracy, which makes it like seem closer to real real font, and many more.
Thank you very much.
Thank you.
Thank you, Yuri, for your presentation. Can you switch to the slide with pipeline, please?
Sure. This one?
Yes, and let us figure out what was done by you, right? So starting from the very beginning, so OCR, you selected existed open source library, correct?
Yeah, we selected existing open source library. We added this
then-
rescaling feature and
So
human
then moving on, machine translation, the same. You selected an existed library.
yeah, model.
Correct? Yes. And then we have the syntax editing. And you used that architecture you showed us.
Yeah,
Yes, this one.
Still.
Based on generative adversarial networks.
Yeah.
And you train it on your synthetic data.
Yeah, we trained it on our trained it on our just dataset. Yes.
Okay, so and so this basically it, and all these 3 main and resize and marriage. It's done by also.
It's like
it's within the
functions inside the OpenCV library. It's
okay. So it's already just to fit into the existing image.
It's like just a step, but it's pretty similar. It's simple.
And can you switch to the contribution slide to sum up? Yeah, so you created this data set. When you stated about EULA, you're talking about this pipeline. Is it
Yeah, I'm
correct?
talking about the pipeline, the framework, which consists of the off-the-shelf models. They are primarily multilingual, so that it can be easily adaptable to other languages and extended. Like the research can be easily based off this pipeline, like further research, different scenarios, different languages.
So the main bottleneck for the to apply this pipeline for Ukrainian, Japanese, like otherwise other direction or other language pairs is actually this GAN network. So others already, other parts of the pipeline already applied to different pairs. So OCR is multilingual and translation.
So if you would want to apply the same framework for a different language pair, then you would need to train your own syntax editing module.
Okay, and for instance, to have this like other way pair from Ukrainian to Japanese, we can use the pairs from the data set, just
we can just switch them. Yeah, we can include them to the training data set to train for both scenarios. It was just again done.
But do you think is it possible to have one model, model that train on both like directions?
On both directions, definitely. We saw with trans, the Hindi and English, they actually do both, but their data set, I believe, consists of like 600,000 samples. We used 150, same as in original Mostel. And yeah, it can definitely be done. We saw some models that actually do kind of multilingual. They include like 6, 7 different languages, but their coverage is relatively small, and they were done.
Can you switch back to this model architecture slide again, please?
Yeah.
So what was the reason to select exactly this? No, not pipeline, but model. What was the reason to select this model?
This is the latest GAN-based model. As I said, diffusion model-based ones are not as relevant because they are not focusing on the syntax editing alone. So this is the latest. It includes all of the best parts from its predecessors and also builds on top of it. Furthermore, it allows for semi-supervised learning. So if we were to add real-world data, we could also like reuse the same architecture to continue training it. And the biggest constraint was also the open source factor, because not all of them are open source.
Thank you.
Okay, thank you, Yuri.
Thank you.
Let's move on. The next student is Tetyana Monchak. She was advised by Nasari Drushchak, and she will be presenting her work entitled Fairness in AI-Driven Recruitment, Analyzing and Mitigating Demographic Biases in Open Source LLMs.
Okay. 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 Can you hear me well? I guess yes. Okay. I will move. Window is best here, I guess. Okay. So the title of my work was already presented. It is Fairness in AI Recruitment. I would like to acknowledge several people and organization. Firstly, it is Grammarly for providing me with the scholarship. Secondly, my advisor Nazari Drushak for his valuable feedback during the whole research process. And last but not least, my husband, because he was keeping me sane during the whole process of writing this diploma. So to the plan, we will start from the motivation, we will review related work, identify research gaps and questions, set the problem. I would describe the experiment setup, data injection, strategies and model selection approach. Also, I will discuss evaluation framework and mitigation techniques, demonstrate the results and summarize this in the end. So let's start with the motivation. Throughout the years that we use and develop AI models, the bias arised in many cases, and it's continuing to appear in different contexts and towards various groups of people, starting from people of different race, ending with anti-Jewish, anti-Israel bias found in the LLMs really like recently. So the topic is important, especially we have a case study where age discrimination was found explicitly in the hiring domain, as well as gender discrimination, and that was found in Amazon tool. So the topic is important to address. Then we will discuss socio-demographic biases in LLM. They appear from historical and structural power imbalances, harms that they introduce are of those two types: representational and allocational. Representational harms including misrepresentation, stereotypes about certain demographics, uneven system performance, derogatory language, etc. Allocational biases, on the other side, they include direct and indirect discrimination. So our model allocates resources unfairly or unequally. Bias can arise in the internal model representations, and also it can emerge during the model's performance on some specific tasks. Bias mitigation and evaluation in LLMs has like the different methods: data level, model level, output level, human involved, and domain specific. Bias mitigation, it depends on which stage of our pipeline we implement these techniques, even pre-model, for example, some prompt engineering techniques, intra-model, which is fine-tuning mostly, and modifying loss function, for example, and post-model when we tweaking our outputs so they would more fair. And like some basic tools that were developed through the years is Equitas AI Fairness 360 and Fair Learn. So in the recruitment domain, bias is found in the job descriptions and job recommendation, in candidate sourcing. LLMs that was found to manifest gender stereotypes is LLMs and transformer models. Roberta Large, GPT, and Llama 70 billion chat. Also, GPT 3.5 Turbo was found to amplify occupational stereotypes related to race, sexuality, religion. So, for example, if religion was given, it would suggest like only some religious occupations. So, I would like also to address the work of my supervisor, Nazari, which is stereotypes in large languages model, demographic biases in hiring decision, as my work is continuation of his work, and we will discuss this later. So in this work, my supervisor uses anonymized data set of job descriptions and CVs, and each CV is injected with one of the 6 protected attributes, which are stated in Ukrainian anti-discrimination law. The model that was tested is GPT 3.5 Turbo. which provides decision, hire or reject, and rationale or feedback, why we should hire or reject a candidate. This work also evaluates counterfactual fairness, which is important, and model reasoning, like how model explains its decision. And this work is tested like various prompt engineering scenarios that we can use. So what are limitations of this work that we would like to address in my work is evaluation framework. It includes some essential metric, but we would like to extend it and enhance it in a way so we have some statistical foundation behind it. Also, injection strategy that was used in his work was a bit artificial and more like non-organic, as it was not introduced as something that candidates describe about themselves, but just as a statement of candidate protected groups. And also we would like to improve like model variety that we tested, because only one model was tested in that researches. So we introduced like here new injection strategy that implicitly incorporates protected attributes. We extend our evaluation framework, which we will discuss later. And also we test a wide range, I would say pretty wide range of open source LLMs. So let's go to research gaps. Research gaps that were identified during the research of the existing literature is that demographic identities are incomplete and US-centric. Representational harms were widely studied, like I said, like stereotypes about occupations and so on. Some derogatory languages, but allocational harm receive less attention. And current research in AI-powered recruitment is based on prompt templates. So we have some prompt like what profession would suit this person, or like which person is more suitable for this profession, and like short description of the person. Like not many works use actual resumes and job descriptions. I would say resume, like some work use resumes, but none of them use like real world job descriptions. So we kind of rely on what model knows about certain occupations. And here we address it via basing our work on real world data. Our research questions are: how do biases in open source LLMs vary depending on the model choice and protected groups of the applicants? Does language awareness of open source LLMs impact their fairness, as we will work both on English and Ukrainian resumes? And how does data injection strategy influence the level of bias in different LLMs? So, general problem setting, we're focusing on allocational harms, which were not studied previously much. Our main responsible AI framework is counterfactual fairness, which states that the decision is fair if it is the same for actual world, in the actual world, and in the counterfactual world that the same like person has different identity, like demographic group. We use our main protected attributes that we will test is gender, marital status, military status, and religion. We use two methods of data injection, explicit and implicit, which we will discuss later. And our models, we took different sizes, which also will be discussed later, is Llama 3, Gemma 2, Qwen 2.5, and Mistral. Okay, so experiment setup is generally looking like this. We take job descriptions, we take our anonymized CVs, we inject them with protected attributes, whether explicitly or implicitly. This creates prompt. When we will go to mitigation techniques, we will also introduce hyperparameter tuning, but for now we pass the prompt to LLM, and the results is decision and feedback. More detail about data injection strategies. We here refer to the technique of incorporating protected group attributes into anonymized candidate CVs. So explicit method was presented already in my supervisor's work, where we just state that candidate's gender, military status, religion, whatever is this sum of, and implicit, we actually like came up with the sentences that are more natural to appear in resumes. So in the context of hiring, for example, here we see like for military status is I'm a war veteran and now look for a civilian job. So we like provide in the context that is relatable to the recruitment domain. Same works like for marital status and religion, which is not like presented here. Also, we aimed to make them gender neutral. For example, we do not say I'm a widow or widower, so model would not assess like the gender of the candidate. So we will not introduce additional bias, but we say, like, for example, my partner passed away, so we don't know like the gender of the person. Okay, let's go to the model selection criteria. We use like 3 main points. Is like the popularity, because it increases probability of model usage in downstream tasks. Like if the model is like not downloaded, it is not used. And second one is instruction tuning, because it is necessary for the high quality output of the model. And sufficient quality of Ukrainian generation text, as we combine both conduct our study for both English and Ukrainian. Here we conducted like small set of preliminary experiments on models to see how they handle Ukrainian text, because like most of them do not explicitly state that they can generate in Ukrainian, but some of them like do the pretty good job. Like they generate fully Ukrainian text, which is logical and okay. So as not really many models can generate text in Ukrainian, we like widened our model selection for English. Here we have like 2 Mistral configurations, 3 Gemma 2 configuration, 2 of Qwen 2.5, and 2 Llamas. And for experiment in Ukrainian, we chose Mistral 7B, Gemma 2 9 billion, and Gemma 2 27 billion. So shortly about evaluation framework. Overall, it consists of 5 metrics, like 5, I would say, parts, because some metrics is much wider than just one metric. So quality metrics, pretty simple, is percentage of valid model outputs, because open source model are more prone than commercial model to produce invalid outputs. Here, like our criteria for invalid output does not follow requested format. So we just have some, for example, advice how to how models should provide output. Like I saw such examples in generation output. Is generated fully or partially in different language, especially actual for Ukrainian. Sometimes like generation is bad for Ukrainian, even if model overall generates okay. And also consists of ambiguous results. Sometimes we have like 2 outputs where we have in one higher, in other reject, and also does not provide any text output. Sometimes we just have symbols, and this is also the case for some models. So the second one is more like domain specific, is acceptance rate. We just calculate like percentage of hired and calculate the percentage of hired, actually. Yeah. The third one is a fairness metric. So we want to explore percentage of non-majority decision. For example, we have one resume. We tested for 5 protected attributes, and we want to calculate the percentage of non-majority decision. For example, if we have like 60% of higher, and for some reason like two were rejected, resume is the same. I would say we want to calculate this percentage. We call it bias, as we just have non-majority decision. So the fourth one is interpretability metrics. We just analyze the cosine similarity between feedback to CV with injected protected attributes that we received during our open source model like examination, and feedback to the same CV but without protected attribute injection. So we just like pass the CVs to the GPT 4.0 and it generated the feedback to that CV without knowing any protected attribute. So we kind of consider this a fair feedback as through concept of fairness through unawareness, when model is unaware of some demographic qualities of the applicant. And the last but not least really is a counterfactual fairness metrics. Here we use permutation tests with 5,000 permutation for our research, where we want to see if I would say our previous metric like acceptance rate, bias, or similarity are significantly different for some protected group. For example, if male are more often rejected from like job application than female. So we will say if this difference is statistically significant. For this, we use permutation test instead of, for example, z-test for proportion, because our sample are dependent. They are not like statistically independent of each other. So mitigation techniques like that are commonly used is pre-processing, in-processing, and post-processing. In our work, we use mostly pre-processing. We use only pre-processing mitigation techniques such as hyperparameter tuning. And we will discuss like the result of using this technique later. So for results, I split it for the model just because like that's like 9 models and they do not fit in the slide. So what we calculate here is a percentage of a protected group with significantly different acceptance rate, either higher or lower significant acceptance rate, similarity, or bias by model and protected attributes. So this is our result. I would like just show all the results and then discuss. These are results for Gemma. These are results for Llama. These are results for Qwen 2.5. And these are for Mistral. Overall, we can see that smaller model perform worse. Like even here, we see like Mistral small 24 billion does not consider barely any bias. But for example, Qwen 3 billion is like heavily biased, especially in the military status. Here is also like observable at Llama, it's just smaller, is also shows more like biased at protected groups, and same applicable for Gemma 2 billion. Also, we can see from these results that gender bias is most widespread. It contains like almost in every model. We see like in Gemma, there's no gender bias, but for example, in the next ones we see like in Llamas, in Qwen, and even like a little bit in Mistral. This one is like most widespread, but military status, I would say, is most intense. We have like large inequality where some groups are heavily discriminated against and some are privileged. So we will deep dive into military status for this explicit data injection. So here's like acceptance rate, and we see that like the most discriminated group here, like blue is significantly below average. So we see that participants in combat action is actually are less likely to be accepted into the position, like in like more than half of the model, in 5 of 9 models, and only Gemma 2 9 billion like giving privilege to the participants in combat action. Civilians, on the other hand, they are more like privileged compared to all other groups that we have here. And also we have some, in some models, we have bias towards like discrimination towards war veterans, and sometimes like not discrimination, but privilege towards war veteran, and small like discrimination against the reservists. Also here we provide range and standard deviation, and we can see that the higher these indicators are, the more biased like groups we have. For example, GEMA 2 billion has a range of 58. So like the difference between civilian acceptance rate and participant in combat action acceptance rate is really significant. So we will move on to quality comparison for data injection, and this where we started our experiments for Ukrainian language, and we observed that our quality dropped significantly. You can see, especially for GEMA 2 9 billion, like for Mistral, it's all right. For GEMA 27, we have slight decrease in the quality. And like, yeah, the main problem here was like the GEMA 2 9 billion. We evaluated it, but this result may be distorted due to this quality issue for this model. So for the result overview of Ukrainian language, we see that GEMA 2 27 billion that had like almost no problem with English language, and bias in English language shows a significant like instability in its performance in Ukrainian language, because we have like more than half of bias group, for example, in acceptance rate for military status. Also, the results are worse for other models, for Mistral, for example, and for GEMA 9 billion. So although like GEMA performed here the best, I would say, results for Ukrainian are like much worse than for English. So here we also like deep dive into military status, and we see like for Mistral the situation is bad. We just privileging such categories as like war veteran, veteran війни, reservist, like reservist, civilian, civilny, and we discriminate, like the model discriminates against військовий пенсіонер. Here, like also age bias can appear just because of the formulation itself. However, we did not we cannot change the protected group definition because of this is like how it is formulated in laws. And for participant in combat actions, also we see that here not always like the worst model has the highest range and standard deviation, but still like this like pattern can be used in English. So here, like for bias, what bias tells us, if the bias is higher than significantly higher, and we combine it with the acceptance rate, for example, for participant in combat action, it means that for this demographic category, the resumes are rejected more often than for others. And for example, if we take reservist and civilian, we see that the model is kind of more consistent with decisions for this candidate. Okay. We'll move on to implicit injection experiments. Here, due to time and resource constraint, we had to select like less number of models. So based on the experiments that we conducted for explicit injection, we decided to like proceed with most biased models and the least biased model. Here we want to test the hypothesis that the most biased model see like this explicit statement, and this signals to use it in their decision, and these explicit statements are also like in the beginning of the text, so can also contribute to attention window of the models, while like larger models have some like fairness settings in them already implemented, but more implicit kind of injection would, I would say, like trick the model. So we want to see like if it's true or not. And our results show that yes. For implicit injection, and English language, we see that Gemma 2 billion perform actually better than in previous experiments for explicit. Same for Mistral 7. But for Gemma 2, like results are significantly worse. I would show the difference, so it would be more understandable, like from the first glance. So we see that many like green rectangles, because the percentage of the biased protected groups decreased, with significant like different in the number. And also we see that like while some groups increased, for example, for religion, it can be explained by the formulation of the statement that was used, because as we should implement the statement that was like related to the context of the hiring, it was stated that as a person is active like participant in religion, and they need like additional holidays for it. So that could be the problem here. But other statements also show that, for example, for Gemma 2, we see that like religion aspect is not really that bad, but military status significantly worsened with change of data injection strategy. And also for Ukrainian, which was 2 models, 2 smaller ones.
Tatiana, could you please speed up, because we are running out of time?
Okay. And we saw like improvements in Mistral, while Gemma 2 9 billion, which was actually like performed better, now performed worse. For comparison of explicit and implicit, we see some like correlation between a number of parameters in the model and percentage of bias protected groups. However, this correlation do not proceed to the implicit injection experiments, because here we see that range of results for larger models is much wider than for explicit injection. So also for mitigation, we use hyperparameter optimization. We use like determined parameters as temperature 0 and top K 1, and we saw like huge decline in quality for Gemma 2 billion, while Mistral is performing like well on this, which is like, I would say, unexpected, because like the aim was to improve the quality with like more consistent outputs. But the results for Mistral, as we do not calculate result for Gemma 2, like not sufficient amount of valid outputs. So the results show that the picture overall is like slightly, I would say, worse than implicit injection by itself, with determined strict hyperparameters, and explicit injection also sometimes better, sometimes worse. I would say like this mitigation strategy is not fit in this case, so we will need to proceed with other methods in the future research. For summary, we found that gender bias is the most widespread across model, while military status bias has largest magnitude. Bias patterns are consistent, so we have military status bias both in Ukrainian and English, but intensity of bias is greater for Ukrainian languages. Negative correlation between number of parameters and percentage of unfairly treated protected groups is feasible only for results of explicit injection. For implicit injection, we see there is no correlation between number of parameters and the bias found in the models. And also implicit injection reveals hidden bias in the model that did not showcase it in experiments with explicit injection, which we see on the example of JEMMA to 27 billion. And also a deterministic hyperparameter setting did not significantly improve the model fairness. So for the future work is exploring in-process mitigation techniques such as LoRa and fine-tuning with fairness-aware losses. Also, it's extending the cross-industry CVs, as we have only CVs from IT industry. We would like to expand to finance and healthcare, etc. And also adapt solution for other domains and tasks, such as, like, for example, scholarship providing and other like decision-making systems tasks. So that's it. Thank you. It's time for questions.
Thank you, Tatiana. It's really important work in the terms of reviewing biases in the existing models. And as HRs, they are really interesting in implementing AI in their business processes. So having this research and publishing it will be really important. Can you go back to your experiment setup pipeline, please?
Mm-hmm.
This carousel is really fascinating.
Many tables. Okay. Yeah. Animation is
yes,
not
this
my
one.
fault. Template.
Okay, so so let's figure out what is going on here. So you have this data set from Genie, right?
Yeah.
And please clarify, so have you updated it since Nazar's work, or have you just used
Reused.
reused? Okay, so it's like a year ago, right? So
yeah.
okay, but I think it's okay. And then, so you have those job descriptions, CVs. You explained to us in many details how you inject those biases, those attributes in those CVs. And then we have this prompt and LLM execution.
Mm-hmm.
So please correct me if I'm wrong, that you create prompt in this way. So there is a job description, there is CV. So please say whether you will have this person to this job. Is this
Mm-hmm.
correct?
Yeah, kind of like this, like with some like output format instructions, and also with system prompt like your AI hiring model system, etc.
Do you have in your work or on your slides, probably in appendix, examples of those prompts?
Yeah, I guess I have an appendix in the tables.
Where in the thesis?
Yeah, not in the presentation.
Can you come in and
yeah.
find out, please?
So lots of appendix tables. Yeah.
Yeah, because it's really important of how you design the prompt, and prompt is part of the equation.
This one is the first one. Yeah.
You're a smart AI hiring system, and your task is to provide a decision on whether to hire or reject candidates for the provided job description. And for each prompt, you have like erased previous session. It's like unique session for each query.
Yes.
Okay. And the same prompt for each LLM.
Yeah.
Mm-hmm. Okay, probably this is it from my side for now.
Thank you very much for your great presentation. Do you remember my disgusting question at the PhD symposium, at the Master's Symposium?
Yeah.
I'm going to repeat it right now.
Okay.
The question is that for me, this work is clearly incremental. Which of your contributions make you stand independently of your advisor?
Okay. The first one is like new injection, and as well, we introduced. I would say like this would be quicker. We introduced counterfactual testing in the evaluation framework. It wasn't introduced. It is based like on the paper in the domain. As well, I changed interpretability metric because we just like Nazari in his work just measured like similarity across feedback that the model provided for one CV, and here we're like comparing to the unfair, not unfair, fair feedback from the GPT. Fairness metric was used like from Nazari, and also like we evaluate the quality because open source models have worse quality than commercial ones, so it is also important to note. And yeah, like something like this.
Okay, thank you. Focusing on your data set, do you think that 450 resumes is a representative sample?
Because of like the nature of our experiments, where we have like many protected attributes, like our 450 resume becomes like 9,000 resume for gender, for example, or like.
Excuse me, how it comes?
I mean, like we have 9,000 runs of a model because we introduced like 20 different protected attributes for each resume. So we have like more runs, not like 450, but like 9,000. Like,
Yeah, I'm asking about the data sample,
the data set,
not about the runs.
So it can be more, but it is actually more because like the data that was provided by Genie contains like thousands of resumes, but as a number of runs is actually like exploding when we add this counterfactual testing that we do. Like just the time constraint and resource constraint does not allow us to test more for now, because like one experiment could take like 4 to 8 hours to run, like for one protected attribute. So we just like did the best we can in this case.
Just to dive a little bit deeper into the pain point, are all these 450 resumes being evaluated over the same set of job descriptions?
Yeah, actually.
So was it a fair evaluation? And this is the question.
Yeah. It's actually like the pairs. Like Nazari developed like small recommendation algorithm that's like paired this job description with CVs. So this pair, they were stable. We evaluated the pair of job description CV. Like this.
How many resumes were evaluated over one job description? On average?
I would say 2 to 3. So we have like for one description, like one.
Isn't it a very small sample size to judge statistically?
It's rather small, but we would like to test like different job descriptions and different resumes, so we would not have like I don't know, half of our sample just same job descriptions and different resumes. So yeah.
And the last question, could you please go to a summary slide?
Okay. My computer does not want to.
Of course, yeah. This is because of the template. Summary, okay. Thank you very much. In my interpretation, please correct me if I'm mistaken, this summary contains mostly negative statements of those with this very limited scope. Why so? Have your work reached the target objective?
The target objective was like actually to see how, like, if we like return to the research questions to see like how these biases spread across models. So yeah, we searched for negative things and we found them. I would say.
And that was the indicator of the success for this work.
Like, I would say the indicator of success is our framework actually like detects any bias. So yeah, like to find what to mitigate in the future, I would say.
Okay, thank you very much.
Thank you very much for your very interesting speech. From my point of view, not bad results. My question is from practical implementation of your ideas. Do you have some connection with the HR agency to implement your ideas? And maybe you have feedback from them.
No, for this research, we did not actually connect specialists in this area. However, we plan to combine these results with the results that Nazari had in this work and publish it as a paper on like but on responsible AI conference or workshop. I do not remember. But yeah, for now, no. But I guess it can be like a future work for this.
Thank you very much for your presentation. I have a question about acceptance rate. We
stay here.
Stay here. What acceptance rate means here? Because when we talk about recruitment, we have few stages. First, HR found resume. Next one, HR sent resume to technical engineer. Then technical engineer say, okay, we can invite. Then technical interview, hard skills, soft skills, job offer. Acceptance rate here.
What does it mean? Actually, this is applicable, I would say, to the stage of resume screening. It is like the area where AI is like hugely implemented right now, and we had like different.
That is the stage that can be implemented automatically.
Yes.
And in slide 20, you have material about interpretability of your result. Could you explain? Maybe
my computer died. I'm sorry.
Deep learning model are highly uninterpretable.
Yes.
What you trying to understand?
Yeah, we will try to try to understand is it at least like similar to the feedback that is provided to the same job description resume pair, but without like injected protected attribute. We also aimed to implement like SHAP values for this to like see what words affect the most. But unfortunately, I implemented that results was not like really interpretable and was not giving me like much information, so I did not include it in the presentation. Actually, this also can be like a future step to choose like more like better fit for a target function for SHAP values. And also these experiments take even more time, so it was a little bit. Yeah.
Thank you very much.
Very short question. You, from the perspective of a real world application of what you did, I bet HRs use commercial models, not open models that you studied here. So can you just...
It can be, but for commercial models, I think it's important, like when you pass the resume to the commercial model, you cannot, I suggest, like you cannot use the API like from the side of the data privacy, because you just give the the private data of the resume to the system. And here the best practice is either like to implement the model on premise, like on some server, or to use open source solutions. I understand like right now it's more about commercial models, but I think open source models could be used for such tasks, possibly with this fairness like mitigation, because the problem is also applicable to commercial models, because like my supervisor tested the commercial model, it also revealed some bias. So I guess like the evaluation of bias is important like for both actually.
I just add here for Rostislav's question that many companies actually in Ukraine, because of the security reasons, they cannot use commercial LLMs, and for that reason they want to use open source to put them on their own servers, and for that reason it's really it's a really crucial question what is Tatiana raised.
I also have a couple of questions. From your slides, from your tables, it was obvious that the larger model is, the smaller is bias, and in some cases there was like zero bias. So why should we ever even care about mitigating if we can just take a larger model and don't care about the mitigation?
Yeah, I'm sorry, my computer died because I just showed a slide where we have this like I would say logarithmic correlation between number of parameters and bias that we found. But for implicit injection, where the attributes are not really explicitly stated in the prompt, the results were worse. Like we saw for 27 billion, we have like much more privileged and discriminated protected groups, especially for military status. So yeah.
Okay, and my next question is that, so in your work, you studied like individual protected attributes. And what about the combination of these attributes? For example, female, war veteran, married religious minority, and so on and so forth. So can you hypothesize how would you approach this?
Mm-hmm. Yeah. This was one of the questions from my reviewer. I remember. So in this study is like one of our limitations. We do not test for intersectional bias because it also like our number of experiments explode with the adding of one projected attribute. With intersectional, it would be even more. So here I think we should introduce like more smart sampling of our data, so we would not test like all combinations, but maybe first and foremost test that the combination that are for like best of our knowledge are more prone to bias. For example, like female war veteran, like or we know that participant in combat actions are discriminated, so we can pair it with other attribute, for example, with gender, which is more prone to discrimination, or with religion, and see like I would say like first construct this like the most prone to bias pairs, for example, if we talk about pairs, and then if we do not find something there, like proceed with the others. I would say like this.
Okay, I see. Thank you. Then, since we are over time, thank you, Tatiana. So let's have a 10-minute break before the next session, and we will start at 11:03.